Hello and welcome to the RAIC Corporate Affiliate Series. My name is Pamela Burke and I am the Education Administrator at the RAIC. Our corporate affiliate for today's webinar is Velux. For over 75 years, the Velux Group has been the world leader in the manufacturing of residential skylights and is one of the strongest international brands in the building materials sector. With over 300 patents in skylight design, Velux is known for innovation, quality, and durability. For over a decade, Velux Canada has been ramping up its commercial product line to serve the Canadian market better. Our commercial program includes the commercial Sun Tunnel Tubular Skylight, the revolutionary Dynamic and Energy Dome Skylights, and more recently, the Velux Modular Skylight VMS, a prefabricated modular skylight design in collaboration with Foster and Partners. Velux continues to lead the residential industry with the no-leak skylight, sun tunnel skylights, roof windows, as well as a range of blinds, installation solutions, and intelligent home controls. Whether your project is residential or commercial, offer your customers the innovation and quality they deserve at an affordable price. For more information, please visit velux.ca/professionals. Today's presentation is titled Designing for Wellness Using Fresh Air from Skylights, presented by Russell Ibbotson. Russell is a professional engineer with 18 years of experience representing manufacturers in the residential and commercial building sectors. Russell spent the first half of his professional career in renewable energy before transitioning into Windows. Russell is now the technical manager at Velux Canada, where his team is responsible for commercial business development, building code compliance, product performance, project support, and after-sales support. Russell has also made volunteering with industry associations part of his job description, including CSC, IIBC, and the CHBA. He is a recognized leader in healthy and sustainable buildings. And now, today's presentation.
Welcome to the webinar, Designing for Wellness with Fresh Air from Skylights. Today's webinar will give you a primer on these topics, and we're going to work to link them together. What is the importance of fresh air? How is that connected to wellness? How can natural ventilation improve wellness? And how can skylights improve and optimize natural ventilation? My name is Russell Ibbotson, and I'll be your webinar host today. I have 20 years of experience in the building industry, working for manufacturers as an engineer, designer, and for most of that time, supporting architectural projects across Canada. I've been with Velux for 10 years now, and I've been monitoring my indoor air quality for 5 years. So I'm not an expert on the topic, but I've certainly spent a lot of time researching it, building my network around this topic, and I hope to share my learnings and best approaches that I've come up with so far in today's webinar. My contact information is here, email, direct to my cell phone, LinkedIn. If you have questions after the webinar, if you're interested in additional information or other webinars that we offer, please reach out to me. We also have a architect learning hub on our Canadian website where you can access some of the information. So today's learning outcomes, at the end of this session, participants will be able to describe the impact and importance of fresh air in our buildings, list some tips and tricks on how to optimize natural ventilation with the use of skylights, compare and select product options for your performance expectations, recognize building design incorporating fresh air from above that focuses on the well-being of people using the space. Now, I work for Velux, and we are sponsoring this month's wellness theme presentations, and we're very excited to do that because it aligns with our values very strongly. Velux has offices in 40 countries around the world. The head office is in Denmark, just a little bit north of Copenhagen, and we're owned by the original family and the foundations which the family runs. And these foundations primarily take a large portion of our revenue and put it out to philanthropic practices like research or cultural development, and a lot of the things that you might see the Velux logo on around the world. Now, we are celebrating our 80th anniversary on April 1st, the day I believe this will be launched. So happy birthday to Velux. At Velux, we really like to think that we know we sell skylights, but we also know that people buy better indoor environments. They buy fresh air, and they buy a view, and they buy daylight. They're not buying a skylight. That's what we manufacture. What they're buying is a better indoor experience. And that's why I think the alignment with talking about wellness and the indoor environment is so important. And this is something that we've at Velux have been talking about for a very, very long time. I mentioned earlier some of the things that we do around the world. We host a website that has a lot of information and celebrates designers, and in this case, we have a photographer, Henry Plummer mentioned there, those who are progressing the practice of designing with architecture and daylight. We have a magazine. We also facilitate a Healthy Homes Barometer in Europe that really takes a look at what can we be doing to improve the health of homes there. Every other year, we host a daylight symposium and a healthy buildings day, and I was very lucky to be able to participate in the last event. It was just a few months before the pandemic started, and myself and my entire family got to present on stage. And I'll let you know why I got to present on stage later on in the presentation. Velux is also a member of the Active House Alliance, and we hosted the 7th Active House Symposium in Toronto just a couple of years ago now. It was a great experience. We also host the International Velux Award. This is for students, and this is worth mentioning because we've had a couple of students do extremely well. Let me be more explicit. A couple of Canadian students do extremely well in this contest. And we also invest a lot in supporting installers across the country. Now, one of the things that I'm really, really proud of, and I have to say, in the 10 years I've been with Velux, this is probably the one thing we've done that's really made the hair on the back of my neck stand up. And I just want to take a minute to talk about this before we jump into the presentation. So in September of last year, we launched It's Our Nature. This is our sustainability strategy for 2030. And the name It's Our Nature has a dual purpose. It's showing that we're taking ownership of nature and that we have a responsibility to nature, but it's also saying that it's in the nature of our company to show leadership in this area. So this strategy for us means a number of things. I'll just give you the highlights right now. We're going to move our entire vehicle fleet around the world to zero emission by 2030. We'll cut flights down by 30%. We're going to move all our packaging to singular and recyclable material. We're working on our circular economy targets. That's a bigger challenge than we anticipated, but we are still optimistic that we'll have those targets out sometime this year in 2021. This one I like. We're working on a 50% reduction in embodied CO2 in our products. And right now, 94% of the CO2 in our products comes from our suppliers. The glass, the aluminum, the plastic, those are the big ones. We've got to work with our suppliers to bring that CO2 content down in our products. So that's a huge challenge. But I've saved the best for last, because the best one is that we're working towards a lifetime CO2 neutral goal by our 100th anniversary. So that's in 20 years. We want to we're going to work with the WWF to recapture 100% of our historic CO2. So not just being CO2 neutral moving forward, we're going to be lifetime. So we're going back all the way to 1941. And based on the scientific calculations, we've estimated that we have produced 5.4 million tons of CO2. So we now have 20 years to capture that CO2 plus whatever else we're emitting in the next 20 years. So this is a really fantastic initiative, and it's one that we are going to be extremely open book about, because we want other manufacturers in the building industry to see what we're doing, and we want to help them match or even better what we're doing. Now, the name Velux comes from ventilation and lux is the Latin word for light. So today, talking about fresh air, this is where the ventilation side comes in. And we're going to tie this to wellness, and that's what today's presentation is. Now, my colleague Monica is doing a similar presentation, but she's going to focus on the daylight side of the company name. So why fresh air? Why am I calling it fresh air? In many places, outdoor air is much cleaner, fresher, and better for you than the air inside our homes. Certainly, when seeing this image of the beach, it just makes me want to take a big, deep breath in, and really enjoy the breeze and enjoy the smells and enjoy the freshness of the air. And that just relaxes me, just visualizing that. So fresh air is extremely important. But did you know that indoor air has been shown to be up to 5 times more polluted than outdoor air? Wow, 5 times. That's a big number. So, where does this pollution come from? You the pollution comes from some of the materials in our house, VOCs or volatile organic compounds. There's things in our house that are releasing fine particulate matter, whether it's our appliances or when we're cooking. Um, we could have radon coming out of the ground into our house, or we could have mold growing because we have moisture in our kitchen or in our basement. And these are all really detrimental to our well-being and to our long-term health. Now, I've got 4 kids, so when I say this, I don't say it lightly. Often, the most toxic, most polluted room in the house is our children's bedrooms. And we have all this stuff in there, and the air quality in those spaces is the worst. So this is something we really need to think of. This is beyond just the design side, but this is taking into consideration on how we select what we bring into our homes. Um, these photos with the glass boxes, they come from a campaign we did in 2019 called the Indoor Generation. There is a URL there, a shorter one, that will take you to YouTube if you want to see the full video. It's very dramatic. It's much darker than anything else we've ever done, but I do recommend it for you if you're interested. And and in addition to the stuff in our house, it turns out that the people in the house are some of the largest contributors to that pollution in the house. We exhale CO2 when we breathe out, and CO2 is what we call a human bioefficant. And CO2 accumulation can contribute to poor indoor air quality. So the average person consumes about 2 kilograms of food and water. I drink a lot of water, and I'm close to 100 kilos, so I'm probably a little bit higher than that. But for comparison, we breathe about 15 kilograms of air. That's a lot of air. We breathe in 11 or 12,000 times a day. Um, so this is a lot of air that we're bringing into our bodies, and our bodies are picking up on any of that pollution that's in the air. So the air quality inside can be bad, and we're breathing a lot of air. And guess what? We're spending 90% of our time inside buildings. And this is a big deal. In the last year, most of us, or many of us that are working from home, have probably spent more than 90% of the time inside. So that potentially polluted air is what we're breathing most of the time, and it can have some impacts on us. So how does this affect people? The short-term effects of poor indoor air quality include dizziness, fatigue, confusion, headaches, nausea, irritation of eyes, nose, and throat. And I focus in on short-term because to me, wellness is short-term. Wellness is how do I feel today, or in the near future, where health is how am I going to feel in years from now. And on the health side, that indoor air quality can affect asthma and allergies and other ailments. But really for wellness, this is what we're focusing on. How is it going to affect us now? It can also impact our focus, our problem solving ability, our productivity. It can make you less strategic, less creative, and more risk adverse if you have bad indoor air quality. And this is a big deal. Think about the boardrooms where companies are deciding the future of their companies and whether they should take big risk or not. Next time they make a big decision, they should consider what's the air quality in here. Are we being too conservative? Classrooms. There's a lot of studies that show that indoor air quality has a big influence on how well kids learn. I have 4 kids. This is an important thing for me. So when you're designing schools, indoor air quality, it has to be an important element of what you're doing. So should we be airing out these spaces? No, that's not a picture of me, but I am the one in the meeting typically that does the long blink or nods my head or drops my pencil. I traveled around for about a year with a portable CO2 meter, and I took it to the hotel rooms with me. I took it to all my meetings in architect offices and around the country. And I started to correlate how much influence CO2 in particular, but air quality has on me. I run the risk of being that guy that fell asleep in the meeting. So this becomes important to me because that's embarrassing. And if we're in a situation where we can say, hey, let's open up a window or let's open the doors and air the room out a little bit, that's beneficial for me. So we now have in my office, in my own office and in my boardroom, I put CO2 meters in. I also put in CO2 meters in all the bedrooms, office, and ground floor of my house, so I can keep an eye on this because it does have an impact. And I'll say after measuring it in hotel rooms where sometimes the ventilation isn't so good, um, it impacts my sleep. Maybe I'm drowsy and I fall asleep faster, but I definitely don't get as good of a night's sleep when the air quality is poor. If you're interested in a little bit more information on this, there are lots of really good resources out there. I'll draw your attention to one because it's some colleagues of mine that support me a lot on this type of work that I do. The Daylight Energy and Indoor Climate Basic Book is available at this link. It's actually a department in our company and the head office. And these guys are mostly postdocs. They coordinate with universities on research. They also help take some of that research and figure out, well, how can we educate people on the importance of indoor climate? So good resource. I recommend you have a look there if you're interested. So coming to the end of this, I just want to do a quick recap. As you see this person who looks like she's really enjoying some good indoor air quality. Indoor air can be pretty bad, 5 times worse than outdoor air. We breathe a lot. 15 kilograms is a lot of air, and we spend most of our time indoors. So we're breathing this potentially polluted air indoors, and this can have a negative impact on our wellness. So when we started off, I used this as a bit of an agenda and a little bit of an overview of the presentation. I've now covered off fresh air and wellness. I'm now ready to move into natural ventilation. So let's go forward. I jumped ahead of myself a little bit. So 3 steps to good indoor quality. So minimize indoor emissions. This is all the materials. This is, some years ago when we were all learning about LEED, we were learning about low VOC paints and the glues that were used. And I remember lots of people saying it's not the smell of new, it's the smell of glue. And that's an indication of the VOCs. So looking at the materials we're putting into projects is a great way to reduce emissions. Keeping it dry, making sure you're venting your cooking and venting your showers and making sure your basement's dry. If it's a residential, of course, in commercial, there's other sources of moisture that you have to think of. But then the next topic is you have to ventilate well, because if you've got bad indoor air, the best way to deal with that is to bring in fresh outdoor air. And how do we get fresh air into the building? Well, there are 2 main types of ventilation, and that's mechanical ventilation and natural ventilation. And mechanical ventilation, it uses fans to pull outdoor fresh air into buildings. And it can distribute them through ducts, or it could distribute them just locally at the fan. It can actually be exhausting air from the building and fresh air be coming in from somewhere else. But really it's using mechanical means, so fans, to move that air. Now this has some pluses because you can increase the size of a fan, and you can add filtration to clean the air as it's coming in. You can add heat recovery ventilation, so you can precondition the air coming in. If it's in the winter time and you're exhausting hot air, you could preheat the cold ventilation air coming in. So that's really beneficial, and it's predictable. And this is why we gravitate towards it, is that a fan, it doesn't matter the outside temperature, the fan's still going to run at the same ventilation rate. So that's something important. Now, the one I want to talk a little bit more about, though, is natural ventilation. And you can have just opening one single window, you can create some natural ventilation, which is really the exchange of indoor and outdoor air. The one I want to spend the most time on is stack ventilation. And this is taking advantage of the buoyancy of air and the differences between the air inside and the air outside. I'll get into a little bit more of that in a moment. So with natural ventilation, we have this stack effect. This is where skylights really do well because you've got cold air or cooler, dry air coming in and that warm, moist air exhausting out the top. And the height does make a difference. Again, I'll come back to that in a moment. The other type of natural ventilation is wind, or the cross ventilation, as we called it in the previous slide. And this is creating a pressure by blowing against the building. And the side that is being hit by the wind is going to have a positive pressure. The other side is going to be negative, and you'll get this air movement in the same direction as the wind. Now, this works on larger buildings. This looks like it could be an institutional building. So you can get a similar effect of that wind benefiting the natural ventilation. And then there's the mixed mode, the hybrid ventilation. And I think this is the model that becomes more interesting for North America, or at least for Canada, where we have the hot, humid summers if you're Ontario, dry or other places in Canada, but you also have some cold winters to consider, and you might not want to open your windows in the wintertime. So this is a model that is worth exploring further. Don't have time to get into it today, so we'll just focus in on the natural ventilation. Now, to give you a little deeper understanding about designing for ventilation, I've picked out 3 standards just to touch briefly on their approach so we can get that little bit of glimpse of understanding. So the first one is Active House. This is one that I've been personally involved with. And Active House, it came out of Europe, but it's gone around the world. And we do have a couple of projects in Canada and a couple more in the pipeline. And it's one I like particularly because of the comfort side. And of the 9 metrics, and there's 4 of them in comfort now in the latest version, and indoor air quality circled at the top there is one of the main design metrics that you're working with this standard. Now, this standard, the design targets are using CO2. So they're using carbon dioxide, which is the main pollution coming out of people. They're using that as the indicator for indoor air quality. Now, that's debatable whether it's a good proxy, to use the industry language. But CO2, if you're in a space where most of the pollution is coming from people, then CO2 is a good proxy. Yes, it does ignore formaldehyde and other things, but if their concentration is less, that's not so important. So it's good to understand that caveat. But they are using parts per million, so that's a concentration level. And to give you a reference point for these numbers, typically, outside is about 400 parts per million. That's what your outdoor fresh air is going to be sitting at. This chart here is giving you an amount above the outdoor level. So that 400 parts per million would actually be 800 if you had an outdoor concentration of 400. And to give you one more reference, typically we say 1,000 to 1,200, depending on the article you're reading, is what they would consider an upper threshold of good indoor air quality when you're measuring CO2. So how do we model for that? Or how do we design with that? One of the options is a software that Velux has that can model energy and indoor climate. So you can take a look at this software and build your model in there. And you can figure out, well, how much ventilation do I need? How much will the open windows provide for me? And then we have ASHRAE. ASHRAE is the American Society of Heating, Refrigeration, and Air Conditioning. And this is what we call out in the building code. So 62.1 is the main one. 62.2 actually isn't called out in the national building code, but the first one is. And I wanted to highlight this one line from the intent of this document. So it's to specify minimum ventilation rates and other measures intended to provide indoor air quality that is acceptable to human occupants and that minimizes adverse health effects. It's like a lot of things in the building code. It's like the legal worst you can get away with. It doesn't say anything about optimizing comfort, optimizing well-being. It wants to minimize adverse health effects. So that's something important because this becomes our benchmark of what is allowable by code. And that, of course, means there's an opportunity. This is your baseline. That means there's an opportunity to have improved ventilation beyond that. And then there's the well standard, and I really like how they've approached it. So they've said, you know what, ASHRAE is well known, it's respected, people are used to it, let's do that. But then we're going to say for larger buildings over 1,000 square feet, you need to use what's called demand controlled ventilation. Demand controlled ventilation, in this case, they're using CO2. And so anytime the CO2 levels and they get higher, the more people or longer they're in a space, as they increase, once they hit that threshold of 800, you either have to turn the fan up to a higher speed or windows are going to open. And I'm like, that's brilliant. What a great way to have combination ventilation. They have some additional considerations for outdoor air quality as well. But I have a number of friends that are contributors to the WELL standard, so it's a very respectable document. And yeah. All right. So I mentioned CO2 and I mentioned ventilation rates, and to be clear, ASHRAE is a bunch of equations, and you understand how you got to set your ventilation rates by room, and for large buildings. And then for Part 9 buildings, for low-rise residential, you're really looking at a air supply number based on the type of room: master bedroom, bedroom, living room, that sort of thing. So how do these equate? And I mentioned earlier that CO2 can be considered the dominant pollution when people are the dominant emitters of pollution in the space. So it's an awful graph. I apologize I didn't take the time to make it a crisper one, but you can see that about 15 CFM or 7.5 liters per second is going to get you about 1,000 parts per million. So that becomes that threshold for air quality. So anything better than that, any more a higher ventilation rate than that should give you a lower CO2. Now I found this other chart. And again, I found these off engineering sites, and I'm an engineer, I'm a professional engineer, but I hang around more with architects, and I'm really into the health side. So I often disagree with these engineering things, and I'll tell you why in a moment. But this chart gives you like an undervented, ideal, and overvented. Now, to give you an idea, and the line moved a little bit. The threshold for well and for active house is 800. So you can see what they're saying in this thing, in this image, is that that's overventilated. Well, how could it be overventilated? Well, when it comes to the engineering side of things, and so much of what the building code now is, with our energy, with our race for energy and energy, full acknowledgement, energy is great. It's closely affiliated with reducing CO2, and we need to do that for the environment, but not at the cost of our health. And this is something that becomes really interesting because it costs money to have more fresh air in a building. You have to condition that air, heat it or cool it or dehumidify it. So on the engineering side, minimizing the ventilation means lower mechanical costs or lower building operation costs. But we know that building operation costs are tiny in comparison to your people cost. So, productivity, it's very easy to make the case that more fresh air increases productivity. It's a good return on investment. Okay, final note on this one. CO2 is easier to measure than ventilation rates. So if you're doing measurement in the space during the ventilation, CO2 becomes a good proxy. The ventilation rates are easier to design for. So that's something to keep in mind. ASHRAE is all upfront ventilation, where both well and active house are looking more at the use of the space. If you're in the space, what happens if you have a party? What happens if, in your boardroom, you've got extra guests in there and the CO2 level, or sorry, the ventilation isn't designed for that capacity? That's why I like the well one. So if you had more people than you exceed the capacity for the ventilation, you have a backup plan. You can shift up to that other gear. Okay. So now I'd like to take a few minutes to just go through some of the, I guess it sounds too big to call them design principles, but I'm going to try to explain some of the stuff that if you read through all the ASHRAE stuff, some of the simplistic stuff that you'd be able to extract from that. So this is a simple building. It's an elevation cross section of a building, and it'll become more apparent when I flip the slide. So here's a building. We've just got two windows. They're equally, the opening size is equal on both sides. I've put them on either side of a building, and you are going to get some airflow through that space. As long as your indoor air and your outdoor air have a difference in barometric pressure, temperature, or humidity, you're going to get some airflow due to the buoyancy difference. Now, if you raise the height of the exit opening, where the air is moving out of, you can change the opening to be smaller. You can reduce the size of that opening because that height difference is giving more push to the air moving out. So let's take that one more step. Oh, I jumped the gun on that one. Let's talk about ventilation area. So ventilation area, in this case, there's two design approaches. In experience, the one on the left comes mostly from Europe, where the one on the right with that actual opening area is typically what we're working with when we're designing for a natural ventilation scenario here, which, funny enough, ends up being mostly on academic buildings when we're working with this, but it's usually the one on the right. So what I was jumping ahead from was that as you make your window higher, you can reduce the opening size and get a comparable ventilation rate through there. So that makes the case that skylights are good for natural ventilation. Now I alluded to the temperature, the humidity, the barometric pressure. So natural ventilation is optimized when the outdoor temperature is lower than the indoor, when the outdoor humidity is lower than the indoor, and when the outdoor barometric pressure is lower than the indoor. This is a case where it's a pressure difference that's driving this buoyancy or stack effect. Hot air rises because hot air is less dense. So lower humidity, lower barometric pressure, all these things contribute to less dense air, and it wants to push up naturally, hence the name natural ventilation. Now that arrow can go in reverse, and I've experienced this in my own house. I have 8 skylights, 5 of which open in my house, and if it is a hot Southern Ontario humid day in the summer, you can feel that warm humid air coming in the top of the skylight and pushing down out the bottom of the house. Now you can further optimize this by creating a stack. So you could actually elevate the skylight to get a little bit more natural ventilation, or a little bit more flow rate through that. However, if you have internal obstructions, it's going to reduce the flow through your building, and you're going to have to increase your openings again. So again, ASHRAE and the European equivalent that Active House uses does talk about the friction of the air going through. So as you constrict the air, it's going to slow down as it goes through. So you're going to need a larger opening to obtain the same ventilation rate. Now, similarly, if you introduce insect screens, it's going to reduce the amount of ventilation rate. Now, my favorite story on this, and some years ago, I saw a presentation on the Manitoba Hydro building. And the presenter, most of the presentation, wasn't great. Us engineers were not always the best presenters. And then he started talking about mosquitoes and natural ventilation and mosquitoes. I'm like, what's he getting at? So on that building, they actually estimated how high do mosquitoes fly in Winnipeg, And at that point, anything above that point, we don't need insect screens to keep the mosquitoes out. So we can optimize our natural ventilation by eliminating the insect screens. So I thought, wow, that is so neat. And that was some years ago. And it's one of those things that's always stuck in my mind when I think about insect screens. So one number that I've read a couple of times is that insect screens reduce the airflow by about 50%. So that's pretty substantial. Imagine that you have to have an opening twice the size to accommodate an insect screen. So what about wind? Well, if wind is going in the same direction as you've designed the buoyancy side or the stack effect, it's going to increase the ventilation as a result. Now, ASHRAE will have you design only based on buoyancy, unless there's a few things. If you're going to show there's a prevailing wind, you'd have to supply some additional support documentation to get that design approved. But you can definitely get it approved with the buoyancy side alone. But the wind in this direction helps the ventilation. If your design is going the other way, though, it could hinder your ventilation. You might have the buoyancy working against the wind. So you're going to have a reduced ventilation as a result. So if you're designing for natural ventilation, it's really important to understand the prevailing wind on your building site, which in some cases is complicated when you're building where there's a lot of obstructions or other buildings or forests or mountains around. It could take some wind studies to understand this part of it. So I mentioned the height. ASHRAE does have some understanding of at different heights you have a different multiplier. A lot of these equations are based on multipliers when you're working through this, so they understand that, and that's going to, the more height you have, it's going to improve the ventilation rate of your design. And what about old buildings? This building is 750 meters from my house. It's my children's school. It is the second oldest school in Ontario. And interesting enough, and I haven't mentioned the pandemic much in this talk, they have kept their windows open all winter, short of the some weeks that they weren't in school. So my kids were doubling up on their ski pants and wearing 2 wool sweaters. They didn't complain about that being cold, but we were very happy understanding this, that they were opening up the windows in the classrooms to air them out, to reduce the risk if one student was sick that the others would get sick. So that's really interesting. Old windows or old buildings like this often don't have mechanical ventilation. My own house only has exhaust fans, and we don't have an intake system. So it's interesting to see. This is, like Europe, where they have a lot of hydronic heating and not necessarily ventilation. Opening windows might become one of your best options. And right along with that, this article was last week in the New York Times, was on the cover of the New York Times, but the animated version of it on their website came out about a month ago, and it's really neat. This is talking about what's necessary to reopen classrooms in the pandemic in New York State. And one of the contributors was Joseph Allen from Harvard, and he was involved with the COGEX research a few years ago that looked at the impact of CO2 on office workers. So some of the things I talked about earlier were verified by his research. But this is I included the URL. It does talk about opening a window or using a HEPA filter. It's an interesting little extra if you're interested. So this is one of the tricky things. How can we actually tell if we need more fresh air? As you enter a space, as you enter a room, you may detect smell, temperature, humidity, or another indicator of poor air quality. But that's because you're changing from one space to another. You've got a comparison. It's much harder to notice poor air quality if you're in the room for a period of time and that air quality is slowly changing. So this is where the importance of having that sensor, your indoor air quality sensor, is really there to let you know, because you've been sitting there and maybe you're getting a little tired, a little less focused, feeling a bit bored, but you don't really know what the air quality is because your body is not a very good sensor. Dr. Kessick did a great paper a few years back where he talked about, humans are bad sensors. And it's true, especially with air quality. So having something, and these consumer products, so you can get them as low as $100 now. It could beep or something to tell you it's time to air out your room. So, there are lots of different products on the market. I can say that I've actually got 3 of these that are on the screen right now. And obviously I've got the Velux one, but I've got 2 of the other ones as well. And they're great for telling you when you need to increase your ventilation. Now this one's really neat because this was one that we collaborated on in Europe. I actually have one on order. I haven't got it yet. But this Airbird, it's tweets and changes its colors that it's shining on the wall when there's poor air quality. So beautiful design, designed with a division from 3XN, the GXN group, as well as Liebcraft, who I've known for some years, and they're experts in sensors in Denmark. And what's interesting about this is that they're doing a pilot project right now in a number of Danish schools. So one of my colleagues who's a postdoc is researching, how are people actually using this in the classroom? And is this benefiting the class? I mentioned mine's on order. Perhaps I'll loan it to one of my kids' classrooms when it comes in. All right. I've mentioned airing a couple of times, so just in case it's not clear what I'm talking about, an airing is a short period of high ventilation rate due to one or more open windows. Ventilation rates achieved from airings are typically in the range of 1.5 air exchanges per hour to 5 air exchanges per hour. So it can be a very effective way to bring fresh air into a space. And I'll show a slide just before the end of the presentation where I demonstrate an airing just with a running CO2 level in the space. But what I've noticed, what I've observed is that when you do a short airing, that the temperature and humidity change much slower. There's more latency, to use an engineering term, in how they change, where the CO2 concentrations, they change quite quickly. So a very short airing would have minimal impact on temperature and humidity, but quite a big impact on CO2. And that's why this works so well. All right, so moving on, we've gotten through fresh air, we've gotten through wellness, we've now covered natural ventilation, and bringing the presentation in full circle, we're going to talk a little bit about skylights because that's what I spend all day, every day working on. So let's start with the residential side. So we have a number of different types of operable or venting unit skylights. So these are individual openings. Some of them can be grouped together and try to make us something similar to a bigger window, but really they're smaller unit skylights. And these products have different installation approaches, and the different ones are popular in different places around the world. The deck mount is more popular in the central to eastern part of Canada, where the curb mount is probably more popular in the western part. And the roof window, which really is European for skylight, is what is the dominant product in our European markets. But we have all 3 available. All 3 will do roughly the same thing. You can size them to get your opening size, and that's what's important for natural ventilation. Now, roof windows, skylights, you can see the kitchen image here, are typically out of reach. We don't live in our attics as much as the Europeans, although I'm in my attic right now, presenting actually from my bedroom. But they're typically out of reach. Where your roof windows, I like to joke that, post World War II, we moved into our basements in North America, and the Europeans moved up into their attics and installed Velux windows. So in Europe, the Velux windows are more like a window because they're within reach. They're just a sloped window. So that's why they're called roof windows there, as opposed to skylights that are up above. But I can say that because a lot of our European products are very innovative and we can get better energy efficiency values with many of them, we're starting to see a larger demand for out of reach roof windows. So even if the people are not going to be opening it up very often, they want that higher efficiency that comes with that window. So we've got some really good options there. Now, I mentioned this one earlier, the Velux active system. This is only available on the Skylights today. We're a couple years away from having it available on the roof windows, but this system comes with a sensor that can measure temperature, humidity, CO2, and sound. Now, it'll actually open the skylights automatically if you want it to, if the temperature, humidity, or CO2 get too high. So mine's set up to do that at home, and I can get it to operate. Um, I can get it to operate and do that. And it's kind of funny because it's like, oh, why is it closing the blinds? Well, it's closing the blinds to reduce heat gain. Why is it opening? And I check in my CO2 meter. I'm like, oh, it's opening because I've hit 1,000 ppm because I don't have a heat recovery ventilator in my house. That's taking care of it in the summer months. I turn it off in the winter because my house is old and it's a bit leaky. So once we get below freezing, I have enough buoyancy, stack effect to bring fresh air in through the cracks in my house. Now this system, this active system is going to be available in the next skylight I'll talk about, hopefully later this year. We're just finalizing some UL certifications on that. But the next product I want to talk about is the one that I spend most of my time on now and my team supports. So this product is the Velux modular skylight. This skylight is a pultruded fiberglass frame. It was designed with Foster and Partners more than a decade ago now, and it's available in all these different configurations, and I'll show you an image in a moment here that really captures all the ones we offer and support in Canada. But this is a product that with the U value and the modularity, it's really coming in heavy for institutional, academic, commercial spaces, and high-end residential. You can see these things have no framing in between the windows, so they come very close together, as opposed to our unit skylights where you have to have the wood framing or the steel framing if it's on a non-residential application. So these are all the different configurations, and you can see each of these images, all but a couple I see, are showing openable venting skylights. So they can be used for natural ventilation. And these products are beautiful. And when they're closed, you can't tell a venting from a fixed unit, so a non-opening unit. We can open every other window. You can't open all of them for structural reasons, but you can still get a lot of ventilation through these windows. And you can see my arrows are showing that warm air exhausting out and the cool air coming in from the sides. Now, as we come closer to the end of the presentation now, here's a case study. This is let me get caught up on my notes here, the UK Hydrograph office. This has 200 skylights in the atrium. So the atrium is along the center spine of this building. You can see where the red arrow is. That is the spine of the building. There are 200 skylights there. Now that design was optimized for daylight and connection to the outdoors, but the natural ventilation was a bonus. So all these offices on the two adjacent wings benefit from having these operable skylights. So you can have the air exhausting out of the atrium and fresh air coming into the offices. And I didn't mention this earlier, but it's important to think where you're exhausting that air. We do a lot of skylight bedrooms. So depending on which province you're in residential, you have the opportunity to have a bedroom that its only window is a skylight, particularly in Ontario, where you don't have to have egress in every bedroom. You can have a venting skylight. So you want to make sure that's not your only exit point, because you don't want the pollution from the kitchen exiting through the bedroom. Again, we want to protect the quality of the air in our bedrooms. So that project, very similar to this image that I showed earlier. We've got this cool air coming in through the windows and the hot, stale air exhausting out of the top. So let's look at another project. This is the Green Solution House. This is in Bornholm, Denmark. That's a small island that is in between Poland and Sweden, but it is part of Denmark. And I was lucky enough to attend the 6th Active House Symposium at this location. And this building, so it's a hotel as well as a conference center. And you can see this fan design is the buildings we see here. And those large windows face northeast. So they're going to get some morning sun when you're in the summer months, but mostly they're looking at north sky. The very bottom one, I'm going to use my cursor here. The very bottom one, when we're looking at the satellite view, you can see there's some more windows in there. I'll show you that one in a moment. And then you've got some small skylights over here. So this is the lobby, or the lobby going into that space. You can see some of the Velux modular skylights, and you can see some even have photovoltaic cells on them. So that's an option for larger projects. So this space is naturally vented. But this space here, it doesn't need a lot of daylight because it's got these large north-facing windows. And I'm sure Monica's going to talk about north light and positioning of skylights in her presentation. I won't get into that, but all we've done here, this design has included some small punched out skylights, unit skylights, or roof windows in this case, because we're in Europe, that are going to allow the fresh air to go through. You're being used for daylight to balance the light with the large windows, but they are used for natural ventilation. And this is also set up so that at certain CO2 levels, they will open. So when we were a full room and we were a couple hundred people in this room, at some point in the morning, I remember the skylights starting to open. You can hear them, the little whir of the motor as they're opening up. And because we were all interested in this, somebody took a reading and was like, oh yeah, the CO2 level is high enough that we need to air out the space. So it was nice, that happened automatically. And before anybody started nodding off, dropping their pencil, giving long blinks. Okay, so we're coming to the end. This is the last project that I'm going to talk about, and it's one that I know very well. This project is in Etobicoke, which is part of Toronto. It was designed by an architect firm called Supercool, and they deserve that name, and it was built by a builder called Great Golf. And Great Golf has been a very big supporter of the Active House program and the early adapter for Canada. This project, and if you take note, I'm in a photo there, my family lived in this house for 6 months, and we blogged and we made videos about the performance of the house and the experience of the house. And that is how I got to go to Paris for the Daylight Symposium and Healthy Buildings Forum, is because of that time I spent there and the work that we did while we were there. So this house was great because those elevated skylights, and you had, and I'm showing the front door because it's the easy place to show where the air can come in. And the front door faced west, and Toronto, the prevailing wind comes from the west. So if you ever wanted to air this house out, you'd open the front door and open the skylights, and you could see stuff almost flying down the hallway. We actually put a bubble machine in and recorded it for one of the videos, so we could have a visual tracker of what of the air movement through the space. It was really interesting. So this works in residential as well as institutional. And if you take notice, if you take a closer look, the most recent edition of the Active House specification has a very similar picture to what I'm showing. So those are my kids that are on the cover of that. All right, so we did a bunch of monitoring, and I really geeked out on this while we were in the house, and I brought all that stuff home, and I've been working with it for the last 5 years. At the end of the 6-month period, we played around with the graphs, and we had only 5% of the time were we over 1,000 parts per million. And that was when we went back with the engineers, in part because I was turning off the HRV and playing around with things and seeing if I could do stuff with the skylights at different times of the year. So I played around with it a lot, which, as much as engineers like to do that, they don't like it when other engineers do that. But that contributed to some of that performance. But for the most part, this is probably twice as good as most new homes. And there's some really good examples of net zero houses in the US where they've monitored the CO2. I didn't include a comparison here. I probably should have, but there are some comparisons that would show that this is a really good performance. Now, this graph on the right is from one of the devices that we had monitoring the CO2. So you can see the CO2 got up as high as almost 1,500, and then I opened the windows. And within a short period of time, that CO2 level dropped down to 600. And then I closed the windows and it climbed back up a little bit. So that's just a nice little visual of how fast that CO2 can drop. And I could overlay to show that the temperature and the humidity barely changed at that time. Okay, we made it. We got through it, and I haven't lost my voice. That's very good. So today we covered fresh air, the importance of fresh air, and we connected the idea to wellness, that fresh air, particularly inside our buildings, is extremely important to how we feel, how productive we are, even how well we sleep. We've connected that with natural ventilation, the importance and the opportunity that natural ventilation has in being part of our ventilation mix to move outdoor fresh air into our buildings. And we've shown that skylights are really good at optimizing that natural ventilation. The learning outcomes, I mentioned these at the beginning. Hopefully I've covered these. It's always hard because I think we came up with these learning outcomes before I built the presentation and we didn't go back and adjust them. So I hope they've met your expectations. Once again, my name is Russell Ibbotson. I'm with Velux. All my contact information is there. I would be very happy if you reached out to me with questions, whether it's on the presentation content, the use of skylights in general, or especially if you've got a project that you would like some design input on. Please reach out. If you don't want to reach out directly to me, a lot of content is put on our Architect Learning Hub. You can connect with us there, and hopefully we can work together. So thank you very much for your time today. I appreciate it. Thank you, RAIC, and I hope all the other webinars go extremely well.
Thank you, Russell, for coming and sharing your knowledge and insight with us today. It is greatly appreciated. For more continuing education opportunities, please visit the RAIC website at raic.org/continuingeducation.